Hello everyone, my name is Fuzuli Akcay and I work at Istanbul Technical University. The current presentation covers determination of ductile fracture loci of two aluminum alloys and two structural steels. The fracture loci are determined using two models: a recently developed energy balance concept and the maximum shear stress criterion. First, I'll briefly summarize the objective of the study and motivation behind it. Next, I'll introduce the theoretical models utilized in the study, followed by the implementation of the models. Fracture loci of 2024 aluminum alloy, 6061 aluminum alloy, ASTM A572 grade 50 steel, and AISI 145 steel are to be determined in the implementation part. The presentation is to be concluded with the discussion of the results and future work. Ductile fracture modeling is critical for a wide range of engineering applications, ranging from large lightweight structures to tiny electronic components. The main goal in ductile fracture modeling is to generate a fracture locus, as the fracture locus provides equivalent failure strain of a material for different state of stress conditions. However, to perform a series of reliable experiments to produce various state of stress conditions is challenging, as well as expensive. Hence, a fracture criterion with a small number of calibration parameters is vital in order to identify a fracture locus with a minimum number of experiments. Therefore, the objective of the current study is to compare advantages and disadvantages of two fracture criteria involving one calibration parameter. In this regard, the energy balance concept and the maximum shear stress criterion are implemented to determine the fracture loci of two aluminum alloys and two structural steels. Ductile fracture models can be categorized as physics-based models and phenomenological models. Physics-based models are generally complex with a large number of calibration parameters, whereas phenomenological models lack physical basis. One of the oldest phenomenological fracture model is the maximum shear stress criterion. MSS criterion was evaluated as the most advantageous criterion with respect to accuracy and the number of calibration parameters in the literature, with only one parameter to be calibrated. Another one parameter fracture criterion is the energy balance concept. KAEB concept is a recently developed physics-based model and is straightforward to implement, in contrast to the most complex physics-based models. KAEB concept is based on continuum modeling of energy release rates, and the concept states that the system seeking a minimum energy state will fracture if the rate of energy change for the system in the fracture mode becomes less than that of the unfractured continuum system. Therefore, the critical state is reached when the rate of energy change of the bulk system is balanced by the rate of energy change of the fracture medium. The critical state equation for the shear mode fracture is given here at the top of the slide. On the other hand, MSS criterion states that fracture occurs when the maximum shear stress reaches a critical value. This critical value is a calibration parameter and is stated as CMMS in the formulation. Here in these equations, sigma 1, sigma 2 and sigma 3 correspond to principal stresses. Epsilon 1 corresponds to principal strain in the first principal direction. Theta F corresponds to fracture angle, mu corresponds to friction coefficient, and C2 is a material constant. As a constitutive equation, power hardening law is utilized, and the strength coefficient, denoted by capital omega, and the hardening exponent, denoted as N, of each material is given in the following slides along with the results. Also, sigma EQ and epsilon EQ represent equivalent stress and strain respectively. The summary of the experimental data is given in the current slide. Details will not be discussed here due to time restriction, and the interested readers in details are referred to a recent article by Zhu and Engelhardt published in 2018, in which experimental results of 2024 aluminum alloy, 66:1 aluminum alloy, ASTM A572 grade 50 steel, and AISI 1045 steel are compiled. Fracture loci of 2024 aluminum alloy determined by KAEB and MSS criteria are displayed in the figure on the left here. Pure shear test, number test, test 11 is utilized to calibrate both criteria. The figure on the left shows that MSS criterion leads to better accuracy if the friction coefficient in KAEB criterion is ignored. However, KAEB criterion becomes superior than the MSS criterion with an appropriate choice of the friction coefficient. On the other hand, neither criteria provide reliable estimations in the case of 66:1 aluminum alloy. Fracture loci of 66:1 aluminum alloy are demonstrated in the figure on the right here, with the first experiment utilized in the calibration, as this experiment is the closest case to a pure shear stress state. The fracture locus determined by KAEB for stress triaxiality dominated cases, that is, tensile mode, is presented as well in the same figure as a red solid line. An additional experiment, test number 4, is utilized in the determination of the tensile mode fracture locus as an additional calibration parameter is needed for calibration. The tensile mode and the shear mode fracture loci suggest that the majority of experiments result in mixed mode fracture, as the experimental data points are confined in between two fracture loci, as can be seen with blue rectangles here. Special cases such as plane stress loading, axisymmetric loading, or plane strain loading are required in order to determine a single fracture locus in two-dimensional space. Therefore, determination of three-dimensional fracture locus is required in complex loading cases, as a single 2D fracture locus does not accurately represent complex loading cases. As an alternative to 3D space representation, on the other hand, fracture locus of different special loading conditions can be represented by a separate curve of each if the fracture locus is presented in 2D space. This latter approach is utilized in determination of fracture loci of both ASTM A572 grade 50 steel and AISI 1045 steel. Again, the fracture loci suggest that the majority of experiments in both steels result in mixed mode fracture, as the experimental data points again are confined in between tensile mode and shear mode fracture loci. Results displayed in the previous slides suggest that mixed mode fracture appear to dominate in majority of experiments, and combination of tensile and shear mode fracture loci in one curve can be more convenient than presenting each of these fracture loci separately. Therefore, a hybrid model, stated in the red box here, is proposed in order to combine tensile mode and shear mode fracture models. As can be seen from the equation, the hybrid model requires two calibration parameters, gamma and C KAEB. Here, gamma determines the contribution of shear in the fracture mode. When gamma equals to 1, the fracture is pure shear mode fracture, whereas gamma equals to 0 corresponds to pure tensile mode fracture. A more detailed investigation of the hybrid model is a topic of ongoing study. Lastly, use of more than one experiment is suggested in model calibration, regardless of the number of parameters required for the calibration, as the choice of experiments utilizing parameter calibration can have a considerable impact on the results. Thank you for listening. And please let me know if you have any questions.